been kind of lying to you for the entire year. A ball rolling down a ramp. How many times have we done it starts with potential energy, it ends with kinetic energy, and so the potential energy at the top equals the kinetic energy at the bottom. Set them equal, solve, get V equals square root of 2gh, right? Well, it turns out that something rotating absolutely has kinetic energy as well, even though it's not going anywhere. Remember, we talk about energy in terms of safety. If I take my bicycle wheel and I get it spinning really fast, you don't want to hug this thing with your face, do you? Okay, that would be unpleasant. So this has kinetic energy. How much kinetic energy does it have? It turns out it's a direct substitution. Instead of mass, use moment of inertia. Instead of velocity, use angular velocity. And you end up with kinetic energy in joules. K equals 1/2 I omega squared. So when an object rolls down a ramp, not only does it gain linear kinetic energy as it speeds up, it also rotates faster and faster and gains rotational kinetic energy. So let's look at a sample problem involving that. With no external work, the work energy theorem becomes the potential energy due to gravity at the top becomes the kinetic energy at the bottom, this time both kinds. Potential energy is mgh, kinetic energy is 1/2 mv squared, and rotational kinetic energy is 1/2 I omega squared. We have to look up the moment of inertia of a sphere. It is 2/5 mr squared. Let's substitute that in. Here we're going to distribute and use the fact that v equals r omega so that r squared omega squared becomes v squared. This allows us to combine the mv squared terms and solve to get v equals the square root of 10/7 gh, not 2gh. It's not going as fast as our earlier calculations would have led us to believe. Some of that linear kinetic energy became rotational kinetic energy. We can make that same extension with work. Work is force times distance. Work on in rotating system is going to be torque times angular distance, torque times angle. Power is just work over time, so divide that by time in order to get power in a rotational situation. There's no such thing as rotational work, it's just work that's causing rotation, right? Okay, work is scalar, so there's no rotational work. Finally, we have momentum. We have regular momentum, P equals mv. Well, we have angular momentum as well. Instead of m, we use I. Instead of v, we use omega. L equals I omega. Nobody knows why it's a capital L. So angular momentum is a really cool concept. It's a really cool topic because unlike your mass, your moment of inertia is really easy to change. All you have to do is change the shape of your body. And angular momentum is a conserved quantity. So L equals I omega. When you make I smaller, omega, your spin rate goes faster and vice versa. Just sit in a chair and hold out something heavy and have someone spin you. And then pull the mass in. You're going to spin super fast. You're going to spin a lot faster. If you stick your arms out, you're going to spin slower. We see this with figure skating when people change the shapes of their bodies too. You've probably done something in your life that shows you that this is the case. We see this everywhere in the universe. We watch gas clouds collapse in space, and as they collapse, they spin faster and faster and faster. Black holes are the most extreme example of that. Black holes can spin hundreds of thousands or even millions of times a second. They're spinning crazy fast because we took all that mass and made its radius smaller and smaller and smaller and smaller. So its moment of inertia got tinier and tinier and tinier and tinier. And so its spin rate just shot through the roof to just mind-boggling levels. Conservation of angular momentum can also be applied with, instead of the impulse momentum theorem, we can have the angular impulse angular momentum theorem. You can provide an impulse by providing a torque times time and solve problems a very, very similar way that we already have. So there you have it. That's circular motion, rotational kinematics, rotational dynamics, and gravity all wrapped up together. We'll do some sample problems and we'll call this chapter done.